in the case of arithmetic sequences, which we talked about last time, basically to go from one number to the next in a sequence, you add a common difference d. In this case, a geometric sequence is you start with a number, right? And to go to each number, each term on the list, you have to multiply by the same number. So for example, suppose, the first term in the list in the sequence is 5. You keep multiplying this by the same number, and that's how you get your term. So for example, multiply by 2, you get 10. Multiply by 2, you get 20, and so on and so forth. That's a geometric sequence. So in the geometric sequence, the ratio, not the sum, but the ratio between successive terms is a common ratio called R. All right? Okay, so in this case, we want to find the common ratio, and we want to find the next 3 terms in the sequence. So here, common ratio, whereas before we had D, now we have R, and it's not A2 minus A1, this time it's A2 divided by A1. So in this case, it's 9 divided by 6, which is negative 3 over 2, which you can also say is negative 1.5. Okay. So that's the common ratio R, and if we want to find the next 3 terms, then we start with the last one here, and we just keep multiplying negative 1.5. So negative 13.5 times negative 1.5 is 20.25. You take that, multiply by negative 1.5, negative 30.375. You multiply that, and you get 45.563. Yeah. Okay? Now, one thing I need you to pay attention to. When R is negative, okay, your terms here are going to alternate sign. Okay? Yeah. Here. Yeah. So these are the next terms, right? So pay attention to that. It's going to be, the signs are going to alternate. Okay, this next one, right, we have terms which are not numbers but expressions. So to find R, we have to divide negative 81n plus 243 by 243n minus 729. And with any rational expression, you have to factor and simplify. From the top, I can factor out a negative 81, and I get n minus 3. From the bottom, I can factor out a 243, and I get n minus 3 again. The n minus 3's cancel. I have negative 81 over 243, which means R is equal to negative 1 over 3. Okay? Now, to find the next terms, you just have to multiply each term by negative 1 over 3. So in the first case, I get negative 9n plus 27. And now I multiply that by negative a third. That gives me 3n minus 9. And I multiply that by negative a third. And I get negative n plus 3. So those are my 3 terms. Okay? All right, so let's do a little exploration then. Suppose I have a sequence, And in that sequence, r is equal to 2. Now, suppose that my first term in the sequence is 5. Okay? So a1 is equal to 5. What would a2 equal to? 5 times what? 5 times 2. And what would a3 equal to? 5 times 2 times 2. And a4 would be? Right. Written in more compact form, this is 5 times 2 to the power of 3, 5 times 2 to the power of 2, 5 times 2 to the power of 1. And if you compare, then, the value of n with these, what do you notice? What is 1 less? The exponent of r is 1 less than n. Okay? So what do you have? You have your first term here. That's the first term, a1, times r to the power of n minus 1. And that is how you find an. Okay? It's a1 times r to the power of n minus 1. So if you're looking for the 30th term, then you multiply by r to the power of 29. Okay? All right, so for this one, it says to write an explicit formula and a recursive formula. For the explicit formula, this is the one we're going to use. It's going to be an is a1, r to the n minus 1. Okay, so what's a1 here? Negative 1. How much is r? We need to find r. It's 2 divided by minus 1, which is negative 2. Okay? That means an is equal to a1, which is negative 1, times negative 2 to the power of n minus 1. Okay? And that is your answer. You cannot multiply negative 1 and negative 2 and get positive 2. Right? Order of operations doesn't allow it. Okay. Okay. Now, the recursive formula, remember that has to look like this. A1 is some number, and then we have an has to relate to the previous term, right? So that has to relate to the previous term, which is a sub what? N minus 1. And in our geometric sequence, what do we do to each term to get the next term? We multiply by r. So that's how it's going to look every time. Now, for this particular sequence, a1 is what? Negative 1. So an is the previous term times negative 2. Okay? But we have to, clean that up a little bit. So we say simply that a1 is equal to minus 1 and an is equal to negative 2 n minus 1. Okay? That's how the recursive formula looks. It's a subscript. This one is a subscript. It's like the a that comes right before. Okay. All right, so let's just get the hang of this formula. We need to find the 11th term, meaning we need a11. All right, if we want a11, then how much is n? 11. And how much is a1? Negative 122. And how much is r? 115.9 over negative 122, which means it is negative 0.95. So an is equal to a1 r to the n minus 1. A11 then is negative 122 times negative 0.95 to the power of 10. We plug this in the calculator, and A11 is negative 73.05. Okay? And you can tell R is negative, so the terms are going to alternate sign. If the first term is negative and the second term is positive, that means all the odd numbered terms are negative. So A11 would be negative, A23 would be negative, right? So you know that you're supposed to get a negative answer for that one. All right. We remember what arithmetic means were? Geometric means are exactly the same thing. Those are just terms between two non-consecutive terms in a geometric sequence this time. All right. So let's find a sequence that has three geometric means between 264 and 1.03125. All right? So, first we need to find R. Okay? To do that, though, how much is n? How much is n? N. How many numbers are there in the sequence? 5. We do know because you have 2 here and we're going to put in 3 more. Yeah. N is equal to 5. And A1 is 264. That means AN is 1.01325. So AN, let me write that here. AN is A1 R to the n minus 1. 1.03125 is equal to 264 times R to the power of 4. Right? So now what do we do to get R? Divide by 264. So 1.03125 divided by 264 is equal to R to the 4. And how do I get rid of that exponent? Multiply or raise it to the power of 1 over 4. And now R is all of this raised to the power of 1 over 4. We plug that into our calculators and we get that R is equal to 0.25. It's just a quarter. That's all it is. All of that is just a quarter. So now, what's our sequence going to look like? We have 264 and 3 terms in between. We just keep multiplying by 0.25. So we multiply once by 0.25 and we get 66. You do it again and you get 4.125. And just to check, do it again and see if you get that number. Do you? You don't? You absolutely do. Okay? All right, so this much about geometric sequences. Geometric series, right, were the sum of all of these. So if I take this sequence and if I put pluses in between, it becomes a geometric series. Just like we found formulas for arithmetic series, we now have to find formulas for geometric series. Just like an arithmetic series, because each step goes up by d, it was easier, right? It sort of makes it easier to find a formula. And here too, each step is the same number times the first, so it sort of lends itself to this cute little formula. We're going to derive the formula, just like we did yesterday. All right. So what we did for the arithmetic series formula was we wrote an expression for Sn, right? Let's do the same thing here. We're going to write an expression for Sn. So the first term is A1, right? And the next term is A1 times R. And what's the next one? A1 times R squared plus dot, 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 plus. Now, the very last term looks like what? It's A1 times R to the power of what? Not infinity, not n. Remember? N minus 1. Okay? The last one is R to the power of n minus 1. And what's the one right before it? R to the power of n minus 2. Good. So here we have A1, R to the power of n minus 2, A1, R to the power of n minus 1. Okay? Now, you know what I'm going to do next? I'm going to take this series, not do it backwards this time. We don't, because in order, like, if you're looking for the last term, which is the 50th term, you multiply by how many R's for the 50th term? 49 R's. So you never actually get to the n. Now what we're going to do, just for fun, is we're going to multiply this entire thing by R. Okay? So let's just do that. R times Sn is equal to what? What does R times Sn equal to? Let's just say it out loud. If I multiply this by R, I get A1 R, A1 R squared, A1 R cubed, A1. So you get the same thing, right? Yes? Okay. So I'm just going to write it again, but I'm going to line up the R's, right? So the first, if I multiply this by R, I get A1R. Rather than write it here, I'm just going to write it here so I can line up the R's. Because the next one then is going to be A1R squared, dot, dot, dot. Okay? And then here, I get A1 R n minus 2 plus, what happens if I multiply this one by R? I get A1 R n minus 1. What happens if I multiply this by R? Times R, that's to the power of 1. What do I get? R to the power of n. So the last term here is A1 R to the power of n. Father of Isaac. Okay. No, that's Abraham, sorry. And then, what are we going to do now? Let's subtract them. We'll add them next time. Let's subtract them this time. All right, when you subtract these, you get Sn minus Rsn is equal to A1, right? Plus, what's A1R minus A1R? Nothing. This minus that is nothing, nothing, nothing. Here, I get a 0 minus this, so minus A1 R to the n. Do you see that? Because these all dropped out. All of those dropped out. Okay? But now, I don't want this mess. I'm looking for what Sn is. So let's just factor out an Sn. And I get 1 minus R is equal to A1 minus A1 R to the n. So Sn is A1 minus A1 R to the n over 1 minus R. And, you know, I don't want to write A1 twice, so let's just factor it out. And look at how cute that formula looks. Okay? That is the formula for the sum of a series. Okay? But now, what if, okay, so check this one out. Let's start with this. Look. Look at this one. A1 r to the n. Right? Look at what we had done here. A1 r to the n. What is that equal to really? A1 r to the n minus 1 times r. So let's rewrite it that way. Okay, over 1 minus r. Okay, now what is this equal to? What is that equal to? It equals to an, right? Look at this formula at the very first page. What is that equal to? Well, first page of this lesson. Look. A1 r to the n minus 1 is what? An. Yeah. See, you weren't expecting that, were you? Yeah. Sn. An times r over 1 minus r. And that is the other formula of this. Okay? So you have two of them. In the second case, it's an is given to you. In the first case, an is not given to you. Okay? That's pretty cool. Yeah. You have to multiply by r because that's just how the proof works. That's just how it's because the geometric sequence is, being multiplied by r, so that's just what we have to do. All right, so here are the two formulas, and now you know exactly where they came from, so you can use them. In fact, we're going to use them right here. Yes. Okay, so the sum of the first 11 terms, meaning we want S11, which automatically means that n is equal to 11. What is r equal to? Negative 6 over 4, which is equal to negative 1.5. Okay? All right, so we want Sn, S11 rather. Are we going to use the first or the second formula? The first one, because we're not given an, right? So formula 1. S11 is equal to A1, which is 4. 1 minus negative 1.5, you assume correctly, to the power of 11 over 1 minus negative 1.5. All right? You plug this into your calculator the way it is. Let me write it again. There's a form for us. So S11 is equal to 4 times 1 minus negative 1.5 to the power of 11, all over 1 plus 1.5, which is 2.5. $140. Okay, so that's the sum of the first 11 of those numbers. Now you could sit there and, just complete the list. 11 is, small enough of a number. You can complete the list. You can get all 11 numbers and add them, or you could just do it that way. Okay? Probably. Okay. All right, find the sum of the first n terms. So we want Sn of the geometric series, that with these given. So you have A1, you have An, and you have R. Which formula are we going to use? Right. So Sn is equal to A1 minus AN times R over 1 minus R. So Sn is equal to negative 4 minus, well, plus really, 65,536 times 2 all over 1 minus 2. And Josh, what do we get here? Jacob? Negative 131,068. The first n terms. Yeah. In case you were wondering. All right. Look at this one now. Okay? All right. Our counter here is going from 3 to 8. So how many terms are there in this series? From 3 to 8? N is equal to, no. 8 minus 3 plus 1. So you subtract these two, and then you have to add 1 because you start counting from the 3. So if you were counting on your fingers, right? It's 3, 4, 5, 6, 7, 8. So really, you can subtract 8 minus 2, and that would be the same thing. It's like when little kids count how many days are left until vacation, but they don't know, like, are they supposed to count today or they don't count today? Well, you're counting today. All right? Yeah. Well, for these, assume that you're always counting the day. Okay? The day that you're in. Okay? So this is that's the distinction between my first and my second son. Like, my second son does it this way now. Okay. Yes, totally. Yeah, so he's using the sigma, accounting for the Shabbaton. All right, so we need Sn. We don't have An for this, right? So we're going to use the other one. We're going to use A1 times 1 minus R to the n over 1 minus R. So we got what n was. What's A1? We could easily find A1 because it's negative 2 times negative 2 to the power of 3 minus 1. Huh? Okay.
Oh, wait.
You get a different N. Book publisher issues. Okay. So this is negative. So A1 is negative 8. Now, what about R? Well, R is the term that you're multiplying with each time. This is always going to be your R. Okay? That number which is being raised to the exponent is your R. 6. Yeah, I know.
There's like the big N and the small N.
There is the big N and the small N. Okay, this N and this N are the number of terms. So how many terms are there in this sequence? When you write them all out, there are going to be 6 terms. Okay? All right, so Sn is negative 8, 1 minus negative 2 to the 6 over 1 plus 2. 168. So these were all finite series, right? These formulas, let me highlight that. This is for a finite geometric series. Well, what if you have an infinite geometric series? Now you're multiplying by the same number over and over and over and over again forever. So clearly now there has to be a distinction. Because if you multiply a number by like 2, let's say, forever and ever and ever, eventually the sum is going to get to be what? infinity, right? It's going to diverge. Eventually, it's going to be infinity. So there has to be a distinction. And that distinction is the value of r. If r, where are we here? If r is greater than 1, then it's going to diverge. Okay? Right? Because like if you keep multiplying by 2 or 3 or 4 or 1.5 over and over and over again, you're going to reach infinity. So we can't figure out the sum in that case. But we can figure out a sum of an infinite series if r, let's say, and this is like the absolute value of r, if it's less than 1. So for example, 1 over 3. Or if r is equal to 2 over 7, and so on. Do you see what I mean? Because in this case, you're not going to get an infinite number. The numbers are going to get smaller and smaller. Do you see what I mean? Okay. So the formulas for the sum can be used to derive a formula again for infinite series. If r is greater than 1, then r to the power of n increases without limit. But if r is less than 1, what happens then? Rn approaches 0 as n approaches infinity. What do we mean by that? If you have r less than 1, right? So suppose your r is like 1 over 3. Okay? And if you raise that to the power of n, okay, what's 1 over 3 to the 1? 1 over 3. What's 1 over 3 squared? 1 over 9. Did it get bigger or smaller? Smaller. 1 over 3 cubed? Even smaller. 1 over 3 to the 100? Even smaller. So as n approaches infinity, 1 over 3 to the n approaches 0. Okay? Math does make sense. All right. So let's derive a formula for the sum. We know that the sum of a series is equal to a 1 minus r to the n over 1 minus r. Okay? Now, we're going to focus on this number. Now remember, this is an infinite series. So n is infinity. So r to the n is what? 0. Okay? So that then becomes a 1 minus 0 over 1 minus r. This is a1. So s is equal to a1 over 1 minus r. Okay? All right, so continuing, we have to find the sum of this one. All right, so first you have to find r, and you have to check if the absolute value of r is less than 1. Because if r is greater than 1, then you can't do it. It's a divergent series. The sum will be infinity. So let's see what r is. R is 18 over 24, which is, okay, so absolute value of r is 0.75, which is less than 1, so that works. Remember, you have to look for the absolute value, okay? All right, so s then is just a1 over 1 minus r. 24 over 1 minus 0.75, so s is equal to 96. Okay? You have to make sure that r, absolute value of r, is less than 1. Otherwise, you can't find the sum of an infinite series, because it'll just be infinity. Okay, what's r here? 0.66 over 0.33. R, absolute value, is absolute value of 2, which is greater than 1, so not possible. All right, or DNE. This is a divergent series. Okay? What about this one here? What's R in this problem? 0.65. Okay, that's R, and it's less than 1, so we can go ahead and find S here. Well, for S, we need A1. Okay? What's A1? It's 3 times 0.65, 2 minus 1. That's the first number here. So this is equal to 1.95. And S is 1.95 over 1 minus 0.65. So S is 39 over 7. Okay? Yeah, this homework is due tomorrow. This was a little tough, I know. Thanks for hanging in there, guys.